Whoops, sorry about that, folks. Here we are. Okay. Greetings and welcome back to our next online lecture in our series of online lectures for CHE 2300. Today we will be discussing in more detail convective heat transfer, but specifically we will be focusing on what is referred to as natural or free convection. And so if you remember from our previous videos, we were dealing with what was known as forced convection, meaning that there was some external force that was acting on our fluid that was causing it to flow, some type of pump, some type of fan, something like that. In the case of natural or free convection, we are referring to convective flow or flow of a fluid due to no mechanical force, no external force that's applied to it. And the fluid itself is moving simply based on density differences which are caused or are a result of differences in temperatures within the fluid. And so in the following schematic, what you see is a heated wall. That heated wall has some length L, and the heated wall is held at a temperature, of T sub W. So if I wanted to look at what both the temperature and velocity profiles of my fluid near that wall, those would look something like this. So let's start with the temperature. We're going to assume that we have a hot wall, so that means we have air out here, and that air is cold relative to the hot wall. So near the wall, our fluid is going to have a temperature that is equal to the wall temperature, T sub W. And as I move further away from the wall, eventually my temperature profile should plateau, and it should plateau to a value of T infinity, which is what the temperature of our air out here is. So we go from a temperature of T sub W at the wall and decrease to a temperature of T infinity far away from the wall. The velocity of our fluid. What does the velocity profile of our fluid look like? It's going to look something like this, where near the wall there is going to be a steep increase in the velocity. There will be some maximum in that velocity, and then eventually that velocity should plateau back to its original value of 0 near the wall, but here we're talking about far away from the wall. If we get far enough away from the wall, the bulk viscosity is essentially 0 as compared to the fluid that is moving due to being directly adjacent to that hot wall. This picture is better drawn, or has been better drawn by someone other than myself, so I'll switch over to that here. Again, we're showing the exact same thing. We have a temperature, we have a wall. It is heated to a temperature T wall, and that T wall is greater than our bulk temperature. So for us, it was TW was greater than T infinity. Wow, I cannot draw an infinity sign today. There we go. And so we're seeing a very similar profile for both the temperature and the velocity, where again, near the wall, the temperature of our fluid is equal to the wall temperature, and eventually we get far enough away from the wall that the temperature of our fluid is the temperature of the bulk. Again, the velocity profile, we start at some value of 0. The wall is not moving. Therefore, our no-slip boundary condition tells us that the fluid directly adjacent to that wall is not moving. But we see this steep increase. We reach a maximum, and then it decreases and levels back off to a velocity of 0 when we get far enough away from the wall. Okay, and so again, what you're observing here is natural convection due to differences in the densities of this air. The air next to the wall is hot, therefore the density of that air is less, so it begins to rise. As that air begins to rise, it cools down. As it cools down, it becomes more dense, it falls, and this cycle repeats where we have this density gradient that is causing circulation of our air, and that density gradient is caused by the temperature gradient that's induced by the hot wall. Okay, so again, free or natural convection. This is convection that is due to no mechanical force. We are not using a pump. We are not using a fan. We can't have the fluid flow at some prescribed Reynolds number. Right? This flow is simply due to buoyancy differences in the fluid, which are induced by the density differences in the fluid, which are ultimately induced by the temperature gradient of that fluid near the wall and far away from the wall. Okay. The heat transfer coefficient at the fluid solid boundary due to natural convection is represented by the following equation. So again, we have our Nusselt number, which is equal to H. In this case, the characteristic length is L. We have some wall of length L divided by the thermal conductivity of the fluid is equal to a constant B, the product of two dimensionless numbers, one of which you know, the other I will introduce you to shortly, and all of that raised to the power n. As you can see, both B and n are geometric factors, and we'll see in a second where we can get those values for B and n. So the first thing I want to talk about is what is that dimensionless number that was just boxed in green. That dimensionless number is the Grashof number. The Grashof number is equal to local acceleration of gravity, beta, which is our thermal expansion coefficient, the density of our fluid squared, multiplied by the temperature difference between the surface, in this case the temperature of our wall, and that of the bulk temperature of the air far away from the wall. This is multiplied by some characteristic length. In our case, this length is L. If this were pipe flow, or we had something where we had a problem involving a circular pipe, then this parameter here would be a diameter. All of that is divided by the viscosity of the fluid. Here I point out that the Grashof number is a ratio of buoyancy to viscous forces, where again our buoyancy is described by this thermal expansion coefficient, and our viscous forces are described by this viscosity in the denominator. We can actually develop another dimensionless number. Please don't forget, we're chemical engineers. We love dimensionless numbers. So I got another one for you. It is known as the Rayleigh number, abbreviated RA, and the Rayleigh number is simply the product of the Grashof number and the Prandtl number. And much like the Grashof number, the Rayleigh number is a dimensionless number that is associated with buoyancy-driven flow. Let me write this out. I said this, but it is L for flat plates. And D for pipes. In this case, I've written it as an L because, again, we're basing our example problem off this heated wall. If this were a heated pipe, and that pipe had some diameter, this would become a D cubed. Okay, last thing I want to point out on this page, the figure 12:8. The way this figure would work, again, more often than not, the goal of our problem is to determine this convective heat transfer coefficient. And so in the problem, you would more than likely be given enough information to calculate this product here, the Rayleigh number. That means you would know the value here on the x-axis. So let's say you calculated it, it was 4. You would then move up to the line and then move over to the x-axis. And you would now know that log base 10 of the Nusselt number is equal to 0.7, which you could then use to solve for your convective heat transfer coefficient. Okay? So, let's define, at least explicitly define, some of these parameters in the Grashof number. Okay, where? We'll stick with green. Where T sub S is the surface / wall temp. Our T infinity is our bulk temp, right, or the temperature far away from the wall. And then beta is our volumetric thermal expansion coefficient. We can calculate this beta based on the following relationship. My thermal expansion coefficient is equal to 1 over my volume multiplied by the partial derivative of the volume with respect to temperature at constant pressure. I can also write this to say the density multiplied by the partial derivative of 1 over the density with respect to temperature at constant pressure. So if I know information about the densities of my fluid at one temperature, if I know the value of my density at temperature A, I know the value of my density at temperature B, I can calculate a thermal expansion coefficient for that particular material. Or for that particular fluid. I'll get it right. Okay, the fluid properties are evaluated at the film temperature. So this is where this class is going to become a bit cumbersome because there are a number of different temperatures that you will need to keep track of. When we were talking about forced convection, the big thing that we thought about or dealt with was what we referred to as a mean bulk temperature, which was simply the temperature of the fluid at the inlet plus the temperature of the fluid at the outlet divided by 2. Here, our film temperature is equal to the arithmetic average of the temperature at the surface or the wall and the bulk temperature. So when I am dealing with natural or free convection, I need to be thinking about things in terms of the fluid temperature. That means back here, when I'm calculating my density and my viscosity, those are all at the fluid temperature, which is the arithmetic average of the temperature at my surface and the temperature far away from my surface that we're calling the bulk temperature. Okay, several factors or several values for the geometric factors B and N are given in the following table. So the important things to point out in this table: one, what type of alignment do you have? Do you have vertical plates or vertical cylinders, or do you have some type of horizontal plates? Right, that's the first thing I need to determine. Once I know that, I know what side of that orange line I need to be on. In the example that I have given, the example here is a vertical plate where my Rayleigh number, or the product of my Grashof and Prandtl number, is approximately 10 to the 6th. So I already know that I am above that orange line. I look at the product of my Grashof and Prandtl number. It is 10 to the 6th, which falls within this range right here. And therefore, I can move over and pull off values for my geometric constants B and N. So for this particular example, if I were to write my Nusselt equation, so the Nusselt number equals H times L divided by the thermal conductivity of my fluid. That is equal to 0.59 multiplied by the Grashof and Prandtl number raised to the 0.25 power. I already know this value because I used it to determine B and N. I should know L, I should know K, and therefore I can now use this equation to determine the convective heat transfer coefficient for my particular scenario. On the last page, I'm going to give you a couple ranges based on dimensionless numbers that will tell you whether or not we have a situation where forced convection is the dominant convective or dominant mode of heat convection, or if free convection is the dominant mode of heat convection, or if it's some combination of both forced and free convection. So to do that, I need two dimensionless numbers. The first is the Grashof number. I divide that by the Reynolds number of my fluid. If that ratio is much, much greater than 1, then forced convection can be ignored. Meaning that the dominant mode of heat transfer is going to be free or natural convection. If that ratio is less than 1, right, much, much less than 1, then free convection can be ignored. Meaning that the dominant mode of heat transfer in that particular scenario is going to be forced convection. If by chance that ratio is very close to 1 or on the order of 1, then I need to consider both forced and free convection when solving my problem. So I have here combined free and forced convection. Okay. Other than that, There's really not much more to free/natural convection. Again, the process of solving these problems, the goal that you're ultimately after for the vast majority of these problems is to calculate some individual heat transfer coefficient and then potentially use that individual heat transfer coefficient to calculate an overall heat transfer coefficient, our capital U value. But the process itself, very similar. Here, I'm just defining now a new equation that I can use when I know that the dominant mode of heat transfer is free convection in my system.